this session I am going to take up carboxylic acids from the chapter Aldehydes, Ketones and Carboxylic Acids. So, you know why carboxylic acids are studied along with aldehydes and ketones. Yes, it is because they have a carbonyl group common in them. So, this is the carbonyl group which is common in all aldehydes, ketones and carboxylic acids. That is why they are studied together. So, anyway, let us confine our discussion to carboxylic acids. So, in this session we are going to study about the nomenclature of carboxylic acids, the different methods of preparation of carboxylic acids and also their physical as well as chemical properties. So, first of all we will see what are carboxylic acids. So, carboxylic acids are carbon compounds having a carboxyl group in them. So, this is the functional group that is present in carboxylic acids. So, you can say these are carbon compounds having carboxyl functional group in them. So, then what is a carboxyl group? Carboxyl group is a carbonyl group attached to the hydroxyl group. So, we have a carbonyl group attached to the hydroxyl group. So, this is called as the hydroxyl group. So, the carbonyl group will have a hydroxyl group attached to it. So, then you say it is a carboxyl group. So, now suppose an alkyl group is attached to the carboxyl group. An alkyl group is attached to the carboxyl group, we call it as aliphatic carboxylic acids, and suppose an aromatic group is attached to the COOH group. So, then we call it as aromatic carboxylic acids. So, now these carboxylic acids, they are present in nature. So, higher members of carboxylic acids having 12 to 18 number of carbon atoms, they are said to be fatty acids, and these are present in natural fats as the ester of glycerol. So, these carboxylic acids are also used in the preparation of many other organic compounds like N-Hydrides, acid chlorides, esters, amides, etc. So, now let us study about the nomenclature of carboxylic. So, nomenclature of carboxylic acid is, you are going to name carboxylic acids, you are giving, most of the organic compounds are given a common name as well as the IUPAC name. So, these carboxylic acids, these were the earliest organic compounds that were isolated in nature. So, that is why they are very familiar with the common names. So, first we will see some of the common names of some important compounds. We will just go through the common names of those compounds and then we will study about the IUPAC naming. So, nomenclature. So, we will take the formula of the compound and we will write the common name. So, these common names, they are derived from the natural source from which it is obtained. So, either the Latin name or the Greek name is taken, it is considered, and we end the common name with IC acid. So, first we will study about few of the important carboxylic compounds and their common names. So, the first member in the carboxylic series is formic acid. So, the common name is called as formic acid, and the Latin name, so this formic acid is derived from the Latin name that is formica, which means ants. So, formic acid is obtained by the distillation of red ants. So, that is why it has got this name. So, we will take another compound CH3COOH. So, this is called as acetic acid. The common name is acetic acid. So, the Latin name from which this name is derived is acetum, which means vinegar in Latin. So, similarly, we will take another compound CH3, CH2, CH2, COOH. So, this is called as butyric acid. This is called as butyric acid because it is derived from the Latin name butyrum, which means butter, which is butter. So, this is how common names are given to the organic compounds. So, but here butyric acid, it is called like this because on so the third compound is butyric acid. It is derived from the Latin word butyrum, which means butter. So, when the butter becomes rancid, butyric acid is formed. That is why it is called as butyric acid. So, this is about some of the important carboxylic acids and their common names. So, next we will go for the IUPAC naming. So, in IUPAC naming, what we do is we replace the E of the corresponding alkane by oic acid, and the numbering is done from the carboxylic end itself because the functional group itself has the carbon atom. So, the first member of the carboxylic series is HCOOH. The common name you already know it. So, it is formic acid, and the IUPAC name is, so the corresponding alkane is methane because there is one carbon atom in it. So, it has to begin with methane and the E is replaced by oic acid. So, you call it as methanoic acid. So, the next member of the series is acetic acid, CH3COOH. So, you know how to write a homologous series. So, you just add a CH2 group to this, you get the next member of the series. So, the common name is acetic acid, and since this has two carbon atoms in it, so then it has to begin with ethane. E is replaced by oic acid. So, you have to continue with oic, leave a space and write acid. So, the next member is CH3, add another CH2 group to it, COOH. So, this is called as propionic acid. The common name is propionic acid, and the IUPAC name is, the corresponding alkane has 3 carbon atoms in it. So, it is propanoic acid. So, the E is replaced by oic acid. So, again the next member is CH3, CH2, CH2, COOH. So, this is called as butyric acid. The common name is butyric acid. So, then what is the IUPAC name? So, it has 4 carbon atoms in it. So, you can name it as butane. E is replaced by oic acid. So, butanoic acid. So, the next member is the isomer of this. So, here you can see the carboxyl group comes first. So, we will have to number it as 1, this as 2, 3 and 4, but here in the IUPAC naming I have not numbered it because the carboxyl group itself has the carbon atom and it is always given a first preference. That is why I have not mentioned it, but if necessary it can be mentioned. So, this compound has another isomer. So, CH3, CH, CH3 and COOH. So, this is called as isobutyric acid as it is branched, isobutyric acid, and the IUPAC name is, so now again you will have to number it because you will have to mention the carbon atom, the position of the methyl group you will have to mention. So, this is the first carbon atom, second and the third carbon atom, the methyl group is attached to the second carbon atom. So, it is 2-methyl the parent chain has 3 carbon atoms in it. So, 2-methyl propionic acid. Okay. So, till now we discussed about monocarboxylic acids, that is those carboxylic acids having just one COOH group. So, next we will discuss about the Iupac naming of dicarboxylic acids. So, these dicarboxylic acids are named in a slightly different way. So, in case of monocarboxylic acids, we replace the E of the corresponding alkane by oic acid, but while naming the dicarboxylic acids, we are going to retain the E of the alkane and we are going to end it with oic acid, but you can use di, tri prefixes in front of oic acid in order to mention the number of carboxyl group present in them. So, the first compound in dicarboxylic acid is COOH. So, this is oxalic acid, the common name is oxalic acid. So, the Iupac name is, since the corresponding alkane has 2 carbon atoms in it, so it has to begin with ethane. E of the alkane is retained and we say it is dioic acid, ethane dioic acid, because it has 2 carbon atoms in it. It is ethane, E is replaced and we call it as dioic acid, that is because there are 2 carboxyl group in it. So, the next member is COOH. We will introduce the CH2 group here, COOH. So, this is called as malonic acid. Malonic acid. So, now there are 3 carbon atoms. So, then it has to begin with propane. Again there are 2 carboxylic groups in it. So, it is propane dioic acid. So, again introduce another CH2 group between the COOH groups. So, this is called as succinic acid. Succinic acid. So, again how many carbon atoms are there? There are 4 carbon atoms. So, you can write it as butane dioic acid. So, the next compound is COOH, CH2 thrice COOH. So, this is named as glutaric acid. Glutaric acid. So, there are 5 carbon atoms in it. So, it should be pentane dioic acid. Pentane dioic acid. And the next member is COOH, CH2 4 times COOH. So, this is called as adipic acid. So, then it is called as hexane dioic acid. So, this is about the Iupac naming of dicarboxylic acids. So, when you come to tricarboxylic acid, we will take a compound and see how it is named. So, in this compound there are 3 carboxylic groups, but they do not occupy identical positions. So, what you can do is you can consider this propane chain and then we will number it 1, 2, 3 either from this end or from this end, and we will say we will name it as propane. The Iupac name is propane 1, 2, 3 3 tricarboxylic acid, tricarboxylic acid, because all the carboxyl group will not have identical positions here. That is why we will not take the carbon of the carboxylic group in the chain. So, that is why we have numbered this. So, propane 1, 2, 3 tricarboxylic acid, and the common name is tricarboxylic acid. So, this is about the naming of aliphatic carboxylic acids. So, next we will go to the naming of some aromatic carboxylic acids. So, you know the first member in the aromatic carboxylic series is benzene ring attached to the COOH group. So, the common name of this compound is benzoic acid. The same name has been accepted by the IUPAC system. So, you can write it as benzoic acid, or it is also called as benzene carboxylic acid. Benzene carboxylic acid, because benzene ring is attached to one carboxylic group. So, it is called as benzene carboxylic acid. So, the next compound will take we call this as phenyl acetic acid. The common name is phenyl acetic acid. So, you can consider to be this to be the derivative of acetic acid, because acetic acid is CH3 COOH. One of the hydrogen atoms is replaced by a phenyl group. So, we have named it as phenyl acetic acid. So, then while giving the IUPAC name, so as we have considered to be this to be the derivative of acetic acid. So, you give number 1 to this and number 2 to this carbon atom. Now, the phenyl group is attached to this carbon atom, the second carbon atom. So, the IUPAC name will be 2-phenyl ethanoic acid, 2-phenyl ethanoic acid. Because there are 2 carbon atoms, it should be 2-phenyl ethanoic acid. So, this is about the IUPAC naming of carboxylic acids. So, next we will go to the structure of carboxylic acids. Coming to the structure of carboxylic acids. Structure of carboxylic acids. So, we know in carboxylic acid there is a carbonyl group, there is an OH group, there is an alkyl group or an aryl group attached to this carbon atom. So, all the bonds attached to the carboxyl carbon, they lie on the same plane and they make an angle of around 120 degrees. They make an angle of 120 degrees. So, it is seen that the carboxyl carbon is less electrophilic when compared to the carbonyl carbon. So, we know this is the carbonyl carbon. So, here oxygen atom is electron withdrawing, it is highly electronegative. So, it is going to draw the pi electron towards itself. So, oxygen attains a negative charge and carbon attains a partial positive charge we have seen. So, you say carbon is more electrophilic, but the carboxyl carbon is less electrophilic. We will see how it is less electrophilic. So, we have a carbonyl group and a hydroxyl group and an R group. So, here again the oxygen is more electronegative. So, it is going to draw the pi electron towards itself. So, then This oxygen bears a negative charge, this bears a positive charge, and now this is linked to the oxygen atom to the OH group. So, now this oxygen has lone pair of electrons on it. So, in order to reduce the electrophilicity of this carbon atom, the lone pair of electron is given here to this carbon atom. So, then the electrophilicity of carbon atom is reduced here. This attains the positive charge. The carbon atom loses its, carbon atom the electrophilicity of the carbon atom gets reduced here, and hence you can write the resonance structure as this. These are the different resonance structures. This is the resonance hybrid of it, wherein the negative charge is being delocalized here between the two electronegative oxygen atoms. So, this is about the structure of carboxylic acid. So, the carboxyl carbon is less electrophilic when compared to the carbonyl group, that is mainly due to the presence of the OH group. So, next we will study about the different methods of preparation of carboxylic acids. So, as you have already studied alcohols, aldehydes and ketones, I think you will be in a position to at least think of some of the methods of preparation of carboxylic acids. Yes, it is from primary alcohols and aldehydes you can obtain carboxylic acids. So, the first method is from primary alcohols and aldehydes. Okay. So, here the primary alcohols, you know, when subjected to oxidation, they give you aldehydes, and this on oxidation will give you carboxylic acids. So, primary alcohols on oxidation gives you aldehyde, and aldehyde gives carboxylic acid, but the reaction might stop at the aldehydic stage. So, it depends on the reagent you choose, that is the oxidizing agent you choose. If you use a mild oxidizing agent, the reaction will stop at the aldehydic stage. But if you use a strong oxidizing agent, the primary alcohol can directly be converted into carboxylic acid. So, we will represent primary alcohol as RCH2OH. So, you can subject it to oxidation in presence of strong oxidizing agents like KMnO4. It can be either in the acid medium, or it can be in the basic medium, or in the neutral medium, or you can treat it with potassium dichromate, or you can also go for Jones reagent, which is chromium trioxide in H2SO4. So, the CH2OH group gets oxidized to COOH group, passing through the aldehydic stage, but the reaction will not stop at the stage. The reaction is, since the reaction will be fast, it immediately forms the carboxylic acid. So, we get RCOOH. So, even long chain primary alcohols like 1-decanol, CH3, CH2, 8 times. So, this is called as 1-decanol. So, on treating it with any one of the reagents, so you can go for Jones reagent, will be converted to the corresponding acid, that is decanoic acid, CH3, CH2 8 times COOH. So, it is called as decanoic acid. So, for you to remember better, you can understand this reaction like this. So, the primary alcohol has a CH2 OH group in it. So, it is undergoing oxidation to form an aldehyde. So, what is oxidation? It is either addition of oxygen or it is removal of hydrogen. So, here you can see there is a removal of hydrogen molecule. So, on removing hydrogen, 2 atoms of hydrogen, you get aldehyde. So, again aldehydes are undergoing oxidation further to form carboxylic acid. So, here an oxygen atom will be introduced. So, addition of oxygen is oxidation. So, an oxygen atom will be introduced here. So, you get carboxylic acid. So, this is how you can remember the reaction. We are not going to going to the details of the mechanism, but you can just remember it like this. So, next method it is from alkyl benzene. Aromatic carboxylic acids can be obtained from alkyl benzenes by subjecting them to vigorous oxidation. So, what are alkyl benzenes? An alkyl group attached to the benzene ring, it is called as an alkyl benzene. So, here I have taken the example of toluene. So, now subjected to vigorous oxidation in presence of KMnO4 in the acid medium, or you can use chromic acid H2CrO4. So, the product will be benzoic acid. Benzoic acid. Here the CH3 side chain, it gets converted into the COOH group. So, the reaction can either be carried out in presence of KMnO4 in an acid medium or in the basic medium. Suppose the reaction is carried out in the basic medium. So, we get the corresponding salt of carboxylic acid, which can be further acidified to give you carboxylic acids. So, we have a propyl group attached to the benzene ring. So, you can call it as propyl benzene. So, now subjected to oxidation in presence of KMnO4 in an alkaline medium, that is potassium. You can take potassium hydroxide, heat it. So, the entire side chain, it gets oxidized. So, the product will be the potassium salt of carboxylic acid, that is benzoic acid. So, this you will have to further acidify it. So, it gives you benzoic acid. So, this is called as the potassium salt of benzoic acid, and this is called as benzoic acid. So, in this reaction, so when you are subjecting alkyl benzenes to vigorous oxidation, the entire side chain will be oxidized to the carboxylic acid irrespective of the length of the chain. So, primary alkyl halides, even the secondary alkyl halides can undergo this reaction. So, we will consider another compound, that is the secondary alkyl halide, that is cumin, or you can call it as isopropyl benzene. So, subjected to oxidation in presence of KMnO4 in an alkaline medium. So, heat it. So, the entire side chain, it gets oxidized. So, it forms benzoic acid. So, if you take a tertiary alkyl halide, aromatic tertiary aromatic benzene ring, So, if you take a tertiary alkyl benzene, so this, if you treat it with this reagent, you are not getting the benzoic acid. That is because this carbon atom has no hydrogen atom to get oxidized. So, in tertiary alkyl benzene, this reaction is not seen because it does not have a hydrogen atom attached to it to undergo oxidation. So, this is about the preparation from alkyl benzenes. So, next we will go for the preparation of carboxylic acids from nitriles and amides. So, what are nitriles? An alkyl group linked to a cyanide group is called as a nitrile. So, this nitrile is subjected to hydrolysis either in presence of an acid or a base as catalyst. We are subjecting it to hydrolysis here. You can use either an acid or a base as catalyst. So, what happens is the RC, there is a triple bond between the carbon and the nitrogen atom. So, this bond is going to break here. So, it forms an amide, RC double bond O NH2. An amide is formed which on further hydrolysis in an acid or basic medium will give you carboxylic acid. So, here hydrolysis is addition of water. You can say it is the addition of water to the triple bond here. So, this carbon atom here, it is going to take the oxygen atom. So, it forms a double bond with oxygen atom, and the two hydrogen atoms, they link to the nitrogen atom. So, they form NH2. So, you get an amide which is a derivative of carboxylic acid. So, carboxylic acid is RC double bond O OH. Instead of OH we have an amine group. So, then we call it as an amide. So, on subjecting this to hydrolysis further, so again you can say see here, this bond cleaves here. The OH of the water molecule, that is OH minus of the water molecule will attach to this carbon atom. So, we get RC double bond OH along with the formation of ammonia. That is because the H plus of water will combine with NH2 to form NH3. So, this is how a nitrile can be converted into carboxylic acid. So, this again will take an example and see this reaction CH3 C triple bond N. So, this is called as methyl cyanide, or you can call it as ethane nitrile, because there are two carbon atoms, it is ethane and it has to end with nitrile because a nitrogen group atom is present. So, subjected to hydrolysis in presence of H plus or OH minus. So, again oxygen will link to the carbon atom through a double bond, and the hydrogen two hydrogen atoms will link to the nitrogen atom to form NH2. So, then further hydrolyze it in presence of H plus, or it can be OH minus. So, the product will be CH3 C double bond O and OH along with the formation of ammonia. Again this bond is going to cleave here, the OH group will link to this carbon atom and the hydrogen atom will link to this nitrogen atom. So, you get carboxylic acid along with ammonia. So, next is from amides. So, we have seen the reaction here. First the nitriles are converted into amides and then amides are converted into carboxylic acids. So, suppose you are given benzamide, and you are treating it with, you are subjecting it to hydrolysis in presence of H plus or OH minus as catalyst. So, what is the product you expect here? So, the product is C double bond O OH, that is benzoic acid. We have taken benzamide here and we have converted it into benzoic acid by treating it with water in presence of an acid or a base. So, this is about the preparation of carboxylic acids from nitriles and amides. So, the next method, it is from Grignard reagent. So, you all are familiar with Grignard reagent, so you know what is it. So, it is alkyl magnesium halide and the general representation is RMgX. So, this Grignard reagent is made to react with dry ice, that is solid carbon dioxide, dry ice, or it is called as solid carbon dioxide. So, now here the alkyl group is electrophilic in nature, that is because it is more electronegative than magnesium. So, this will have a partial negative charge on it and the magnesium atom will have a partial positive charge. So, now this R group acts as a nucleophile and this is going to attack the carbon atom of dry ice. So, again here the carbon atom of carbon dioxide, solid carbon dioxide, is electrophilic in nature because it has two highly electronegative oxygen atoms on either side of it. That is, this oxygen can draw the shared electron towards itself, this can also do it. So, this attains a partial positive charge. So, the R group will attack this carbon atom. Simultaneously, this oxygen atom will have a partial negative charge. So, this is going to attack the magnesium halide. So, the product will be R C double bond O OMgX, we get an additional product. So, this on hydrolysis, here the bond is going to cleave here. So, the hydrogen atom of water will link to the oxygen atom and the OH group of water will link to the magnesium halide. So, the product will be R C double bond O OH along with Mg OH and X. So, this is how you can obtain carboxylic acids from Grignard reagent. You can write an example for it, CH3 magnesium chloride you can take. So, methyl magnesium chloride, treat it with C double bond O and that is carbon dioxide, solid carbon dioxide. So, this methyl group will attack this carbon atom, this oxygen will link to this magnesium halide and the product will be CH3 C double bond O OMgCl. So, in the next step this bond is going to cleave, subjected to hydrolysis, the product will be CH3 C double bond O OH and Mg OH and X. So, in this way you can obtain carboxylic acids from Grignard reagent. So, both nitriles as well as Grignard reagents, they can be prepared from haloalkanes. For example, we have CH3Cl. So, you can convert them into, you can convert methyl chloride either to a nitrile or you can convert it to Grignard reagent, that is CH3MgCl, or here you can obtain CH3Cn. How will you get a nitrile from CH3Cl? So, suppose we have taken methyl chloride, we treat it with potassium cyanide, so then we get methyl cyanide. So, if we treat it with magnesium in dry ether. So, then we will get methyl magnesium chloride. So, then again you can subject them to hydrolysis in presence of an acid or a base. Here you can treat it with carbon dioxide, that is solid, CO2 or dry ice. So, here the product will be CH3. This on subjecting it to hydrolysis further followed by acidification will give you CH3 C double bond O OH, and here also you get CH3 C double bond O OH. So, here the carboxylic acid obtained will have one carbon atom more than that of the starting haloalkane. So, then in case you want a carboxylic acid with greater number of carbon atom from the starting alkane, you can go for this method. You can convert haloalkane either to nitrile or you can convert it to Grignard reagent, and if you get a nitrile subjected to hydrolysis, this you can treat it with solid carbon dioxide. So, you get carboxylic acid with one carbon atom more than the haloalkane. So, the next method, it is from acyl chloride and N-Hydrides, acyl chlorides and N-Hydrides. So, what are acyl chlorides and N-Hydrides? Both are the derivatives of carboxylic acids. So, acyl halides or acyl chlorides are represented as R C double bond O Cl, and N-Hydrides are represented as R CO twice O. So, we will take R C double bond O Cl, that is acyl chloride, and we will subject it to hydrolysis. Will subject it to hydrolysis. Now, Cl minus is a very good leaving group. So, this is going to be replaced by the OH minus of water, and so we get R C double bond O OH along with HCl. So, here we are subjecting it to hydrolysis. So, since chlorine atom, that is Cl minus is a very good leaving group, this will be substituted by OH group. So, we get carboxylic acid. So, suppose the same reaction is carried out in presence of a base. You are carrying out hydrolysis in presence of a base. So, then you get the carboxylate ion, and this has to be subjected to hydrolysis. Acidification. This has to be subjected to acidification to give carboxylic acid. So, again we will take an example. We will take acetyl chloride CH3COCl. This is called as acetyl chloride subjected to hydrolysis. So, the product will be CH3 C double bond O OH along with the formation of HCl. The same reaction you subject it to hydrolysis in presence of a base, that is OH minus. So, then we get the carboxylate ion along with Cl minus. This on acidification further will give you acetic acid. So, we have started with acetyl chloride and we have ended up with acetic acid. So, next we will study the preparation from N-Hydrides. So, I have told you the general formula of N-Hydride is RCO twice O. So, we will take benzoic N-Hydride. R is C6H5 CO. This I will split it and write C double bond O O C double bond O C6 H5. So, in subjecting this to hydrolysis, so hydrolysis is again the addition of water. So, water has OH minus as well as H plus in it. So, this OH minus is going to link to this carbon atom. So, again this carbon atom has 2 oxygen atoms on either side of it. So, they are highly electronegative. So, this will have electrophilic character. So, this will have a positive charge on it, partial positive charge, that is why the OH group will attack to this carbon atom. So, oxygen atom will link to the H plus ion. So, the product will be C6 H5 C double bond O OH and C6 H5 C double bond OH. So, we get 2 molecules of benzoic acid from benzoic N-Hydride. Similarly, we will take another compound C6H5 C double bond O C double bond O CH3. So, this is called as benzoic ethanoic N-Hydride. Benzoic ethanoic N-Hydride. So, we have the benzoic group and the ethanoic group. So, benzoic ethanoic N-Hydride. So, subjected to hydrolysis. So, here again the OH group will attach to this and oxygen along with the bond will link to the H plus ion. So, we get 1 molecule of benzoic acid and 1 molecule of acetic acid. So, when N-hydrides are subjected to hydrolysis, we get the corresponding acids. The next method, it is from esters. So, you know what is an ester. So, an ester is formed by the reaction of carboxylic acid with alcohols in presence of a dehydrating agent. It can be a mineral acid like sulfuric acid or phosphorus pentoxide. You get an ester along with water. So, you know that reaction is called as esterification and it is a reversible reaction. So, we will represent ester as RCOO, R dash. So, both the R groups can be alike or they can be dissimilar. So, subjected to hydrolysis in presence of an acid. So, if you subject it to hydrolysis in presence of an acid, we get R COOH and R dash OH, which is the reverse of esterification reaction. So, we will take an example for it. We will take ethyl benzoate. Ethyl benzoate subjected to acid hydrolysis. So, this is a reversible reaction. So, here again we have H plus and OH minus. So, this OH minus will link to this carbon atom and the oxygen atom along with the bond will link to the H plus. So, the product will be a benzene ring with a carboxyl group attached to it and C2H5OH, that is ethanol, and this is benzoic acid. We will take another example. CH3, CH2, CH2, C double bond O C2H5. So, this is called as ethyl butanoate. So, this is the butanoate group. So, ethyl group is attached to it. So, this is called as ethyl butanoate, subjected to hydrolysis in presence of a base like sodium hydroxide, in presence of a base. So, then again here the OH minus of water, or here since we have used a base, NaO minus will attach to this carbon atom. It is going to displace OC2H5. So, OC2H5 will link to H plus. So, first we get the salt of the acid CH3, CH2, CH2, C double bond O, ONA plus C2H5OH. So, we get the sodium salt of butanoic acid. Sodium salt of butanoic acid is formed. This on acidification will give you butanoic acid CH3, CH2, CH2, C double bond O and OH. That is, the Na will be replaced by the hydrogen atom. So, we get butanoic acid. So, these are the different methods by which carboxylic acids can be prepared. The first method was from primary alcohols and aldehydes. The second method was from alkyl benzenes. Then it was from nitriles and amides. The fourth method was from Grignard reagent, and the fifth method from acid chlorides and N-Hydrides, and finally it was from esters. So, next we will have to study about the physical properties of carboxylic acids. Aliphatic carboxylic acids having carbon atom up to 9, they exist as liquids and they have an unpleasant odor. They have an unpleasant odor, but those carboxylic acids having carbon atom greater than 9, they are wax-like solids, and they are odorless as they have low volatility. They have low volatility, so they are odorless and they are wax-like solids. This is when the carbon atom is greater than 9, and if they have carbon atoms up to 9, then they will be in the form of liquids and they will have an unpleasant odor. So, coming to the boiling point of carboxylic acids. The boiling point of carboxylic acids is high when compared to aldehydes, ketones and even alcohols of their comparable masses. That is because the carboxylic acid molecules, they undergo extensive intermolecular hydrogen bonding. So, there is a lot of bonding in carboxylic acids through hydrogen atom, that is hydrogen bonding takes place, and even in the volatile state the bonds cannot be broken. So, carboxylic acids exist as dimers even in the volatile, in the vapor state. So, you can see the dimer here, this is carboxylic acid. So, here we can see the dimer of carboxylic acids. So, the oxygen atom of one carboxylic acid will form hydrogen bond with the hydrogen atom of another carboxylic acid, and here again the hydrogen atom will form bond with the oxygen atom of another carboxylic acid, and they exist as dimer. That is, both the molecules will be together and it is not possible to break this bond even in the vapor state. That is why we say the boiling point of carboxylic acid is very high. And then coming to the solubility of it. So, carboxylic acids, that is simple carboxylic acids having carbon atom up to 4, these are soluble in water. But when the number of carbon atoms goes on increasing, the solubility goes on decreasing. That is because the carboxylic acids or these molecules will combine with the water molecules and they will form hydrogen bond. So, up to 4 carbon atoms it is alright, but when the R group, when the length of the R group goes on increasing, number of carbon atoms increases, there will be a hydrophobic interaction of the hydrocarbon part, and that is why the solubility goes on decreasing.